Hello everyone, I'm Rieko. And first of all, I appreciate organizers for giving me opportunity to present our latest work. And today, I'm gonna talk about how galaxy properties depend on the local matter density or the cosmic wave, which is known as the environmental effect, based on not galaxy distribution, but on the matter density itself. And I start my talk from the brief introduction of galaxy evolution. Okay, so understanding the process of galaxy evolution as well as quenching is one of the unresolved questions in galaxy evolution. Statistical studies of past decades have unveiled that the these processes mainly drive galaxy evolution. And one process is called the internal process. It includes any phenomena depending on or is linked to the galaxy's mass, such as stellar feedback, supernovae, and AGN feedback. So those phenomena induce or suppress star formation by accumulating or expel the interstellar medium. In contrast, another process called external process or environmental effect includes any processes caused by the interaction with the surrounding gas or galaxies, such as galaxy mergers and land pressure stripping. So this process is especially true in dense regions like galaxy clusters and groups. So both of these processes actually help shaping galaxy properties and lead to star formation quenching. But which process dominates in galaxy evolution is a debated subject. So in the local universe, the environments are known to play a critical role in galaxy evolution. So as you may know from this plot, observations have identified the strong dependence of galaxy morphologies and their colors on the environment, in the sense that the more blue and star-forming galaxy found in field, in contrast, more red quenched galaxies are found in clusters or dense region. So those observational proofs indicate that star formation history is heavily influenced by the cosmic environment. Then the question may arise, when those environmental effects appeared. So one key period of this question may be cosmic noon, because that time is the peak of star formation history, as you can see from this figure in the universe, and galaxies shaped what they are like today. However, previous studies on cosmic noon have been studies on environmental effect at the cosmic noon have been inconclusive. So some studies suggested that the internal process plays a dominant role. So for instance, this study shows that star formation rate at redshift 223, marked by this black circle, do not depend on galaxy overdensity. In contrast, other studies observed environmental effect by showing the decline of star formation rates depending on the galaxy overdensity, as I highlighted line in orange and green. So one of the reasons for these inconclusive results could be the challenge of estimate in the galaxy overdensity. So normally, galaxy environments are assessed by galaxy distributions through different estimators, such as Carnegie smoothing, nearest neighborhoods, and friends of friends algorithm. However, Those different estimates give wildly different overdensity estimate, as you can also see these 3 plots, which might lead to discrepant conclusion over studies. Besides, using galaxy distribution itself poses some challenges, especially when we estimate galaxy overdensities at higher redshift. For instance, we may miss many galaxy overdensities with Fuzzy-based galaxy distributions because Fuzzy galaxies could dim the true density contrast due to the large uncertainty of Fuzzy estimate. The higher mass completeness limit may also cause selection bias toward overdensities where many high mass galaxies may reside. In addition, it's still difficult to correct the observational selection function by traditional environmental measures such as those estimators, even with spectroscopic data. So in order to overcome those challenges and correctly evaluate the galaxy environments, we refer to the underlying matter density itself, which determines the galaxy distribution. Then we investigated the environmental effects in the real universe. So for that purpose, in this study, we use 2 matter density maps, namely TERDIS and COSCO. So those 2 data reconstructed the density field in the cosmos field at redshift 2. So as Ben talked on the Monday morning, the TERDIS reconstruct the density field through forward modeling techniques from the Lyman alpha tomography map and 3-dimensional galaxy distributions. On the other hand, another reconstructed density field, COSCO, is a suite of constraint simulation designed to resemble the 3-dimensional galaxy distribution in the cosmos field. So those 2 reconstructed density field at TERDIS and COSCO have a trade-off between spatial resolution and the volume. So TERDIS has a finer spatial resolution than COSCO, but only covers a portion of cosmos field due to the limited survey footprint of the Lyman alpha tomography map. In contrast, COSCO reconstructs the density field of the cosmos field almost entire footprint. So using those 2 reconstructed density map, we checked the consistency of our results. So based on the density field of TERDIS and COSCO, we evaluated the galaxy environment in those 2 ways. So one method uses a local overdensity contrast delta, which is a ratio of local density to the cosmic mean. So this approach would tell us the dependence of galaxy evolution on small-scale environments of a few comoving megaparsec. So in this study, we refer to the matter density within 2 comoving megaparsec diameter around the galaxies. So another approach looks at the cosmic wave to see the influence of much larger scale in the galaxy evolution. So for that purpose, we classify the cosmic wave into 4 structures, void, sheet, filaments, and a node from low to high density. So the components of the cosmic wave were characterized in terms of deformation eigenvalue and eigenvectors. And we and for this cosmic wave method, we only use TERDIS because of the higher spatial resolution than the COSCO. So as for the galaxies, we use the ones above the mass completeness limit and with spec-Z measurement. It's because the reconstructed density maps of 30s and Cosco have a higher spatial resolution than for the uncertainties. So that's why we only use the galaxies with spec-Z measurement. And then our final galaxy sample used in these studies are shown here. So using those number of galaxy sample, we assess the dependence of star formation rate, specific star formation rate, and the fraction of special type of galaxy, which are shown in here. The stellar mass and the star formation rate of our samples were referred to the Cosmos 2020 catalog. And also a specific assumption. Today, I will focus on presenting the results. But if I have a bit of time in a discussion, I would like to show the fraction results. But anyway, then I move on to show the results. So the first is to the local model density. Okay, so there are the median of star formation rate and a specific star formation rate as a function of model density contrast delta. So we divided our galaxy sample into two based on their stellar mass, with the threshold is 10 to 10.5 solar mass, and examine the dependence of the density. And blue is for low mass sample, and red indicates for the high mass galaxy samples. And we consider the results reliable if both these 30s and Coscos results show the same trend. And before I talk about the dependence result, one notable thing I'd like to first say that we could present the galaxy properties even in, maybe this is better, in the low density region below delta equal 1, as well as the over density region. Okay, then I'd like to talk more about the dependence things. So as for the dependence of the environment, we found two common trends in the 30s and Cosco. The first is to low mass galaxies. So they show a comparable median values in both star formation rate and a specific star formation rate, regardless of density. It indicates that the mean star formation activities of low mass galaxies are independent of their local matter density. The second common trend that we found was in the high mass galaxies. So their star formation activity are the same within the error bar below delta equal 4 or 6. However, this beyond this threshold, they show a sudden drop in star formation activity by a factor of more than 30. So it's a very different tendency from the low mass galaxy sample. So it implies that although the mean star formation activity in high mass galaxy would be independent in low density environment, they get lower in high matter density region. So we also looked if we could see the same trend in the main sequence diagram when we divided our galaxy sample into 4 based on local matter density. And here are the results. A different color indicates the different densities of the sample. And blue one is the lowest density, and the red one is the highest density. Then we found that the density subsamples were consistently distributed within the error, except for the massive galaxy being in highest density subsample. So such massive galaxy in the highest density subsample show a sudden drop of star formation activities. So again, we found that star formation activities decline more only in high mass galaxies at dense region. Okay, then next, I switch to the topic of the dependence on the cosmic web. And again, we classified the cosmic web into four for region of the void, sheet, filament, and node. So first, we examine the entire trend in the Byron plot. So different color indicates the different cosmic web structures. So then we found that all structures but void show a similar distribution with long tails towards lower star formation activities value. However, when we compare the main distribution overlaid as this box plot in the center, it shows about the same in all structures. It means that the entire distribution in star formation activities seem to be comparable, independent of the cosmic web structure. So these trends could be more clearer in the main sequence diagram for individual structures. And color usage is the same as the one in this middle Byron plot. So then, what we found that all structures have the compatible value in both star formation rate and specific star formation rate within the error, independent of the cosmic web structure. So indicating that less dependence of star formation activities on the cosmic web structure. So because the density also depends on the distance from the node, we also examine the dependence of the median star formation activities as a function of a distance from the node center. So in this study, we define the node center in the following manner. So first, we extracted the node, and then we identified the highest density pixel within the node region and regarded them as a node center. Then galaxy properties were examined as a function of a distance from node center. Again, a blue and a red color indicate the low and high stellar mass subsamples. Then we found two common trends in both star formation rate and a specific star formation rate. And one is seen in low mass galaxies. So it shows that their star formation activities values are the same regardless of the distance. Oh, yeah. And the other trend, so second trend, is seen in high mass galaxies. So similar to the low mass galaxies, they also show the similar star formation activity values beyond the 2 cubic megaparsec away from the node center. But both star formation rate and specific star formation rates suddenly drop when they closer to the center. So, this distance investigation indicates that median star formation activities usually do not differ in distance from nodes. However, high mass galaxies seem to suppress their star formation when they are very close to the node. So summarizing our star formation activities results, we found no dependence of star formation activities in low mass galaxies on both small scale and the large scale of the cosmic web. On the other hand, high-mass galaxies show a drop in star formation activities at high-density region or toward a node, although their star formation activities are about the same in low-density region. So those results conclude that generally, environmental effects are not the main driver of galaxy evolution of redshift 2, but they appear to be an environmental effect on galaxies with high mass in dense environments, and this suppresses their star formation. So then, what kind of phenomena is expected for the suppression of star formation in high-mass galaxies at dense region? So one possible explanation could be the overconsumption of cold gas. So this phenomena is expected to occur in high-mass galaxies in denser environments. So generally, the gas depletion time is proportional to the ratio of gas mass to the star formation rate. Since the star formation rate proportional to stellar mass and redshift, this depletion time gets shorter in high-mass galaxies than in low-mass galaxies in case of the same amount of gas. Meanwhile, gas mass can be determined by the balance of circular outflow and the inflow. Some cosmological hydrodynamic simulations have suggested that the gas accretion rate is suppressed in denser environments, showing a significant drop in accretion rate in environment. And this is one example of the simulation results. And red color indicates the result of the high density environment, and the blue one shows the low density environment. Then we found that this gas accretion rate in the high density region show drop comparing to the low density environment over the all stellar mass range. So that leads to a shorter depletion time in galaxies in denser environment than in lower dense one. So those two situations can simultaneously occur in high mass galaxies in high density environment. Then star formation will be even more suppressed than the one with the same stellar mass in lower density environments. That is called the overconsumption. So the sudden drop in the star formation activity found in our results, our sample in dense environments may be the proof of this overconsumption of gas reservoirs. Okay, this is a summary of my talk. We investigated the environmental effect of galaxy evolution based on the matter density itself for the first time at redshift 2. And then we obtained those results. However, we actually suffer from large uncertainties due to the limited sample with the SPEC-Z estimate. So we will extend this study with the PFS survey and hopefully give solid conclusion in the future. Okay, thank you very much.
Thank you. Questions? So let's start.
Hi, that's really nice. I was wondering about when you define the web, do you use the Hessian definition? I think that you use to define your web. You use the eigenvalues of the because if you used like disperse or something, that would give you more precise location of the filaments, but it won't give you their size. It'll just tell you points for nodes and lines for filaments. But I wonder there if you could get closer to filament, because there'll be a lot of regions that are filaments that may not have much of an effect. And for the nodes, it looked like you were sort of finding a size there at about 2 megaparsecs, which might you might have picked that out with what you're seeing. No.
Okay, yeah. Actually, we didn't use any other kind of identifier of the cosmic wave yet, so maybe it's good to check. Yeah, thank you.
Thanks for that. I have a comment really rather than a question. I really enjoy this massive galaxies using up their fuel fast. And the reason is because I spent a lot of time working on submillimeter galaxies, and in particular recently protoclusters at higher redshifts than redshift 2, where the simulations do not contain enough star formation in the cores of the protoclusters. And loads of my colleagues spend all their time talking about quenching, but what I need is the opposite of quenching. So I mean, it's clear to me that you need to turn the knob up in the densest regions in the earlier universe, which is exactly what you were talking about. So I'm really happy to hear this part of your talk. So thank you.
Hi, thank you for talking us through this so well. Really enjoyed that. I would like to link this a bit to what I was talking about earlier, with the caveat that you're at much higher redshift. So let's see if it's worth it to consider that the previous environments that these galaxies were in. So how does the relation of the star formation activity relate not only to the current environment, but to what it has been before? For example, you said really close to the nodes, this is where the star formation activity drops. Now, in the much nearer universe, I would say so close to a node, these are the backsplash galaxies that have been affected by the cluster, and we can see that the overwhelming majority of them are quenched because of this. Is this something at redshift 2 to think about, or is it completely different mechanics there?
Yes, I'm not sure it could be the answer of your question, but one thing I think related to your talk is, oops, sorry, this one. So this is actually the, so what I skipped today. So this is the result of the fraction of some special type of galaxy as a function of density or cosmic wave. So this is a density result though. Then what we found was we didn't find any mergers in a submillimeter galaxy in the very dense region. However, in contrast, AGN quiescent galaxies are found in dense region as well. So it means like, it sounds like, of course, as I said, this result is just obtained from galaxy with specti. So still we have large uncertainty, but if it is true, we can expect that galaxies may experience pre-processing even at redshift 2. So they spend their kind of mergers or submillimeter phase in intermediate density region, and then while they're traveling to the more higher density region, they changes their phase to the AGN quiescent, and finally they get into the cluster center. But once they arrive the cluster center or cluster more dense region, they also affect the additional environmental effect, as I talked about the consumption, overconsumption. So that what I saw is that may happen in redshift 2, but again, this is kind of still tentative. So yeah, I want to check if it is true with more larger sample with PFS in the future.
And this is really great. Just a quick question: how the mergers? How did you identify them, or are you sure that these are mergers? How did you get there?
Yeah, actually, we didn't identify merger by ourselves, so we just cross-matched the merger catalog in the Cosmos region. So there is some merger catalog is already public, so we just cross-match our spectri catalog to that merger catalog, and if there is one, we consider them as a merger. Yeah.
Okay, because that's also a difficult thing to
Yeah.
identify.
But they would have both have spectrum for space.
Oh, yeah.
Excellent. I understand. Thank you.
Thank you for that great talk. You showed star formation as a function of distance to node centers. I'm wondering if you also did also analyze star formation as a function of distance to filament spines.
Yeah, that aspect must be very interesting, but I didn't check it, so yeah, it's gonna be a future work. Yeah, my kind of homework. Yeah.
Thank you.
Thank you.
And then the last question.
Hi, great talk. I was just trying to reconcile or trying to make sense of your results in the context of Olivia's talk yesterday, which mentioned that at redshift 0 we have void galaxies being younger and bluer and more star forming, and in your case it seems that it doesn't really depend on the environment all that much unless they're massive. So, is that a redshift 2 versus redshift 0 effect, or do you maybe have any insights?
Do you mean the
Or maybe
colors?
I'm misunderstanding something.
No, it's fine. Yeah. Do you mean the dependence of the colors, or?
Well, the star formation rate, as a function of like the environment density. So.
Yeah. So if our result is true, one thing I can say is this redshift 2 does not have strong impact of the environmental effect. So that's why basically, unfortunately, we didn't check the color on the density, but maybe let's say even the color or star formation activity, the cosmic wave or density does not affect, because mainly environmental effect is not the main driver of galaxy evolution at this redshift. But if it's more getting the current universe, the situation may change. So that's why at the local universe, we can find the clear environmental effect as I show in the introduction. Yeah.
Okay, thank you.
I think we should break for lunch and thank everybody who spoke this morning. Thank you very much.
Thank you.